Okay, I think we can start. Everybody is now joined, I think, who is going to join. So good afternoon, everybody. Thanks for joining this IMechE webinar presentation on battery energy storage. First of all, I'd like to just give an introduction to our presenters. Blanboz Smart Renewables. So a short introduction is that Blanboz delivers cutting-edge battery energy storage solution advisory solutions, blending technical expertise with innovative engineering and commercial elements to maximize performance and client returns, with over 20 gigawatt hours of battery energy storage projects deployed worldwide. Blanboz transforms energy storage into a powerhouse of efficiency and profitability. Andreas Blanco is the founder of Blanboz, a successful startup. Like I said, major consultancy for working with major consultancy firms, developers and transmission operators, working globally with technical advice and engineering services in project feasibility, feed, development, construction, commissioning, operation, and maintenance of solar and battery energy storage. Harry Thompson is the Blanboz project consultant with over a year of experience in the renewable energy sector, specializing in battery energy storage projects. He is an associate member of the Institute of Mechanical Engineers in the UK and is currently working towards obtaining his chartered status. Harry has developed a keen interest in energy storage through his honours project on future electrical grids, and since then he has worked as both a battery energy storage engineer and assistant project manager, evaluating over 3.8 gigawatt hours of battery energy storage tenders to help clients make informed technical and commercial decisions. Additionally, he has expertise with DCO hybrid battery energy storage and solar PV projects. So without further ado, I'd like to hand over to Andreas and Harry for their presentation in this webinar. Thanks, Andreas and Harry. Over to you.
Thank you very much, Jonathan, for the introduction, and thank you everyone that have joined us today. So yeah, today we're gonna have a brief talk of the overview of the battery energy storage systems, and Jonathan mentioned, and Andres Blanco, Managing Director of Blanboz, and with me I have my dear colleague Harry Thompson, Best Project Consultant. So we are gonna be talking about the intro to BESS technologies, technical parameters. Harry is going to be taking you through the BESS designs, an overview of quality and assurances and investment costs, a bit of the commercial key elements, and I'm going to be discussing the current market and a bit of future of BESS. Then we're going to be wrapping up the session, and we're going to have a dedicated time for questions and answers. So please, guys, use the Q&A option from Zoom if you want to pop your questions. So please sit back, relax, and enjoy it. So getting straight into it, we're going to be discussing into the BESS intro and technical parameters. So the first thing that we need to understand is why the need of energy storage. So we are going to have conventional thermal plants retiring and larger penetration of renewable energy system, both at distribution and transmission level. So what that means is it's going to bring a lot of imbalances to the grid and to the electricity operator, because having the thermal plants not supporting the grid through synchronous machine and having penetration of renewable energy assets for the like of solar, wind, that brings intermittencies with them, imbalance the grid quite considerably. So that's why batteries are becoming quite essential for not only to balance the grid in terms of how quick they can respond, but also to the net CO2 targets that the UK wants to achieve. I don't know if you know this, but there are strong ambitions that actually the national grid, the electricity operator in the UK, they want to have the grid free of fossil fuel by 2030. And this is going to be only possible by the use of energy storage, or actually battery energy storage, and also to support the bit of energy security. At the same time, moving into the BESS chemistry, and we have the lithium iron phosphate, or as we know it, the LFP. This is the most common chemistry used in battery projects. Obviously, you also have the nickel manganese cobalt, or NMC, or other type of chemistry, but the most common type that has been heavily commercialized as of today for battery energy system is your LFP. So lithium is an alkali metal, group 1 of the lithium family in the periodic table, highly nuclear unstable. Its atomic number, it has 2 electrons in the first inner layer and 1 extra electron on the outer layer. This extra 1 electron is the one that it always wants to share, because its on stability, it always wants to keep sharing this electron. So it's very abundant but finite resource, mainly in Chile, Argentina, and Bolivia. This is what we call the lithium triangle. And the lithium comes in these areas kind of in a brine, what we call lithium pools. But you can also find it in Australia, Uruguay, and the Republic of Congo. And the lithium comes in this area more embedded within the rocks. And it can also be found on the deep sea. You can see that I mark it there in red because deep sea is very controversial. We really don't want to be disturbing the deep sea, because it's not only issues with contamination, which is your key one, but at the same time geopolitical tensions. But it's estimated that actually the resources of lithium in the deep sea is even more abundant than the above sea. We have been working with battery over 100 years. I don't know if you know this, but a fun fact, actually, the first car being invented was electric cars. This was actually invented before internal combustion engines by Thomas Edison. But for whatever reason, it didn't work and wasn't too efficient, but that's for a different debate. It took us over to the late 1970s and beginning of 1980s, through the research of Stanley Whittingham and Sir John Goodenough, who sadly passed away recently, to discover the benefits of lithium ion in the spectrum of batteries. Then Akira Yoshino and Sony found a way to commercialize this through their equipment and portable equipment requiring batteries. So to give you an idea of how battery cells work, you first need to have you're going to have your cathode, which is your positive element, where you're going to have your metal oxide, iron phosphate in this instance. Then you're going to have your anode, the negative side. In lithium iron phosphate batteries, normally we use graphite, and the graphite is going to work. Imagine if you were to have a car park where you have all of your car very well organized. This is what the anode do for the lithium ions when they move through. And then you're going to get the division between the two, cathode and anode, what we call the electrolyte, which is an aqueous solution for this type of batteries, with chemical compounds, sodium chloride, nitric acid, to name a few. If you were to connect this cell into a source, then you're going to be injecting electrons, and obviously these electrons are going to repel this extra electric negatively charged ion from the lithium ion, and the positive is going to be being attracted. And obviously there you reach an equilibrium, and that's when your battery is pretty much charged. If you were to connect a multimeter, you're going to get around 3.6 to 4.5 volts, which is the nominal voltage of a battery cell. Lithium ion, even though that are very efficient in terms of electrochemical storage, at the same time they are very sensible to degradation. There are different parameters, but the key one is your solid electrolyte interface, or what we call the SEI. The SEI, pretty much because this little chap, the lithium ion, has to go from the cathode to anode through the aqueous solution. It's going to create a layer around this lithium ion, which is going to impact the properties to exchange that extra electron. At the same time, we have external issues like longevity of the cell, high temperatures, high current, voltage, which are external abuses or impacts on the batteries that is gonna ultimately have an effect on the capacity in terms of energy and power through the time. And this is what happens with your mobile phone when you buy it, and after 5 years, no, we hold the charge as when it was new. The same happens with battery. Normally, batteries with lithium ion will last anything between 6,000 to 10,000 cycles. In terms of years, it's going to be anything between 10 to 15 years, obviously, depending on the use. So to give you an idea of how the BESS is, its composition of the terms that we normally use, you're going to have your battery cells. So they come in different shapes. Cylindric pouch is like a little bag, and then you have your prismatic shape. Nowadays, you will see that it's most common to use the prismatic shape because of its cooling properties. It's easy to keep temperatures uniformed through all of the different cells when we add the cooling system. Then we put these cells connected in series and in parallel to increase the current and the voltage, encapsulate them, and that's going to be your battery module. You then put your battery module on top of another one, and you create the rack. Also, you increase your voltage here. And then you have all of these racks together within an enclosure. And this is what we call conventionally your battery container. Very important piece of equipment, your power conversion system or PCS. PCS, I don't know why, don't ask me why, is the convention name that has been used for batteries, but pretty much it's the same converter or inverter that you're used in the solar world. The only difference is that this has to be bidirectional because it's going to charge and discharge. We can have multiple levels of converters, and the more levels or bridges, the more efficient they are, but also has an impact on the prices. So the most common type that you're going to see between central and string inverters is going to be two-level converters. And what we have there is your filters and transistors that are going to pretty much hit the flatness of the DC current, and by opening and closing very fast and changing the flat into sinusoidal curve. And if you were to put an oscilloscope there, by having the two bridges interacting, you're going to have your upper bed, and then you have the reverse current open and closing again, and you're going to have your bottom bed. And obviously through time, you're going to have almost a perfectly or even perfect sinusoidal curve. That is the one that you need for AC to synchronize with whatever equipment you have or with the grid. The key thing here is the materials used in the PCSs, in the transistors, which are the ones pretty much key driving the cost. So you're going to have your isolate gate bipolar transistors, or most commonly known as the IGBTs, made by silicon. The only challenge that we have with these materials is the heat dissipation, and that's where you tend to see chunky units and to have a space, and also force cooling to have a space for this heat exchange. The technology is moving to the silicon carbide metal oxide semiconductor field effects transistors, or easier just to say MOSFETs. However, it's not heavily commercialized and the costs are still a bit high. The two things that I really want you to get away from the PCS point is that you're going to have two types in terms of functionality. You're going to have your grid following, which pretty much requires the grid to sense the voltage and the frequencies to operate. If there is a blackout or whatever happens, your PCS is going to shut down. And then you're going to have your grid forming. The grid forming is the key pretty much. I want to use the word magical because it's very important, and it's going to be what is going to change pretty much history for any renewable energy asset and batteries. Why? Because if you remember that I mentioned that the thermal plants are going to be retiring, they have moving parts, synchronous machines that their provisions to support the grid is not going to be there. Now we can do that with the grid forming. The grid forming basically, it can create its own voltage reference and frequency. That means that it doesn't require the grid and can support the grid reference point to other equipment connecting there, whether if it's a microgrid or even to support the grid when there are blackout events. You may have heard the issue that happened in Spain, Portugal. I still don't know what was the actual issue, but my first gut feeling was that there was a lack of inertia, because this is very common. To control inertia is very difficult, and inertia pretty much comes from synchronous machining. So the beauty of having the grid forming now is that we can control that by supplying inertia from this grid forming equipment. You may hear out there virtual or synthetic inertia or virtual synchronous machine, and I know that many electrical engineers don't like that term, but anyways, the key point is that you're going to have your grid following, grid forming. Actually, in the UK, grid forming has been accepted by the grid code. I think that was last year. So I'm sure that in the near future, all of the projects are going to be mandatory to have grid forming capabilities. So in the context of BESS projects, we have the BESS works, which is pretty much what is supplied by where we have the battery containers, where we have the MBS kit or the PCS transformer and whatnot. Anything else, a part of that is going to be your balance of plant works. Is a contractor that's going to do the civil, connect everything together, to then the grid works, which is the electricity operator, a distribution system operator that is going to interconnect everything. So fire and explosion issues. This is very controversial topic, and I just want to check what is your, let's say, view on a question or a questionnaire that I have here for you to select. So please feel free to select what you think are how many incidents that led to fire happened in 2024 in around 100 gigawatt hour worth of BESS projects. So it's ramping up. I'll give you another few seconds. Oh, it's muy fast. Okay. So I'm gonna end the poll there. So yeah, surprisingly, because I actually put the answer just to catch you there. It was 8, and the point there, obviously, this is by EPRI. This is an organization that is tracking all of the fire incidents and that related to fire safety as well. As to how the A was calculated, that's not for me. But the point is, and the message that I want to say is that actually fire and explosions are very unlikely in battery projects. That doesn't mean that there is a risk. Actually, there is a major risk there. But the thing is that the technology has been evolving quite considerably in terms of safety, and how that's why now we're in a position, especially new equipment, that are quite robust in terms of fire and explosion safety nets to prevent this risk to happening. And it's not, I need to be careful how I say this, but the point is that we need to be sometimes careful how the media portray fire events, and we need to go and investigate as to what actually happened that led to that fire. So the key phenomenon here is your thermal runaway that will lead to fire. So as I mentioned earlier, batteries are very sensible to external abuse. This is how we call it. It can be in a form of electrical by overcharging or undercurrent, over voltage, under voltage. Mechanical vibrations are very critical to batteries, and thermal as well, whether if you are operating your system in very high temperatures or very low temperatures as well. This will lead to internal short circuit between the cells and the anode cathode, and also short circuiting between the battery cells and the surrounding equipment. And what is going to happen then, that you're going to have the thermal runaway event, which is going to lead to fire. And your fire and chemical reaction is a little bit different than your conventional fire triangle. Why? Because you have an exothermic reaction. And that exothermic reaction, what it means, it creates its own heat. It fits its own heat, which is a fundamental issue for firefighters when they need to put the fire off in battery projects, because literally almost nothing, I'm not a fire expert, but almost nothing will put the fire away apart of discharging the battery. So the thermal runaway is going to there are going to be different stages that you're going to run the thermal runaway. So the first one is you have that SAE decomposes in an exothermic reaction, and this can occur at 90 degrees with temperature increase of 0.001670 degrees Celsius per second. And you're going to see how the temperature start increasing quite fast. Then an exothermic reaction between the intercalated lithium ions and the electrolyte starts, and this can occur at 130 degrees with temperatures increase of 0.40 Celsius per second. And finally, you're going to have an exothermic reaction between the positive material and the electrolyte takes place. So pretty much here, your cathode start a short circuiting between the electrolytes, and also it's going to start short circuiting between the anodes as well. So it's a total chaos here. And this can occur in temperatures above 200 degrees, and with a temperature increase of anything between 1.7 to 17 degrees Celsius per second. As you can see, the temperature of the fire is going to increase very rapidly, and that's why you tend to see the chemical fires, or particularly those in batteries, are quite aggressive. So here I just want to give you an indication in terms of timing, because when something is being picked up as to when the fire happens, you don't have much time. So in this particular event, something was picked up at the 3rd minute, and you see there from 3rd minute to 13 minutes. That 13 minutes is very vital, because that's when your battery cells are going to start off-gassing. These battery cells are the ones entering in a thermal runaway, are going to start off-gassing or venting. Pretty much what that means is combustible gases are being generated and released to the within the battery container. From the off-gassing to fire, actually you don't have much. It's around 10 to 13 minutes. That's why we need to rely on sensors to have, first of all, to alert us and to have some precautions of how we can minimize, hopefully, the fire, that it doesn't happen, or to reduce the risk, and also to alert us to trigger the emergency response plan. Explosion, very important. Sometimes it's forgotten around the issues with fire, and it's only fire the one that takes all of the attention. For me, it's very critical. We have been involved in different projects that have had issues with explosion. The risk is obviously slightly lower than the risk of fire, but because now we have gas suppression being used, gas fire suppression being used in battery containers, it increases the likelihood of explosion. Back in the day, we used to have inert gases or nitrogen, and you have to remember that these containers, battery containers, are quite airtight, so the system can be highly pressurized very quickly. And if you add on top of this your combustible gases, it can be ticking bomb there. And nowadays, you will see more often the compressed aerosol, which is a mix of gas and potassium salts to reduce the concentration of oxygen within the combustible gases. And you can also see or either forced or ventilation or vents that allow natural ventilation to trying to release those combustible gases to the atmosphere. These are not mandatory currently, depending on the local authority, but by guidance, they are not mandatory. And that's why you remember when I mentioned the 13 minutes and the point when the cells start venting is very important, because here is when we can add sensors, combustible gases detector, particularly hydrogen, because that's the highest concentration that you will get when the battery start venting, that you can detect early enough to trigger any safety mechanism before the fire. So your explosion window is likely to happen, obviously, through this off-gassing event, and these normally happen before a smoke, when the cells are being burned, and before the fire. So why don't you rely on safety standards? So you're gonna hear a lot of the NFPA 855 and the NFPA 68 and 69. These are American standards, by the way, but have been widely used in the industry. The NFPA 855, if you're kind of master standard, the top level standard, and the 68 and 69 are more related to explosion. Currently, the NFPA 855, we have the version 2023, which is being revised, and the new one is coming next year. But the 2023 version gives you as an optional, or either the 68, which are your little vents that I showed you in the previous slide, whether if it's forced or natural ventilation, or having computational fluid dynamic designs analysis done on your system. The new version actually is going to be mandatory that you need to have forced ventilation and you need to do your CFD analysis on your system. Then we get other American standards that have been widely used, the UL 9540A test methodology and the UL 9540 certifications. These tests, what it does is to trying to see the thermal runaway between the different components in a battery system. You start by burning the cell. If the fire propagates, you go to the module, so on the racks, and then finally your container. Also important, UL 1973, these are certifications and tests done at battery cell level. Then you have your UN 38.3, which are safety tests done to the batteries to being able to be transported either by sea, air, or land. So now let's move to Harry, who is gonna delve deeper on the BESS design, quality and assurance, and commercial points.
Thanks, Andres. Yeah, I'm going to get straight into the design and talk about the products that are available at the moment. So to begin with, typically we're seeing that batteries are being shipped in transportable containers, which house the cells, modules, and racks, as well as the ancillary systems, such as the cooling systems, power electronics, and the battery monitoring systems. At the moment, we're seeing two solutions offered. This is a DC block partnered with a central ECS, and an AC block partnered with string inverters. As you can see here with the DC block, with depending on the project configuration, 1 to 4 containers connected to that central ECS. Then we have the AC block. The output of this block still within the container is AC, so it's ready to go and be compatible with the grid. It still needs an MVPS or an MV transformer to connect to the correct grid connection voltages, but it means that inverters are housed inside the block. We're seeing an interesting trend where more than ever before, there's more AC blocks available in the market and from more suppliers. This is changing how we're seeing tenders, which is increasing competitiveness, but it also affects how ECS providers are affecting their prices, as without the DC blocks, there's less demand for them. I'm now going to speak about separation distances that we see on battery projects. This is coming from standards previously mentioned, such as NFPA 855, as well as our own experience with projects, and dealing with lenders and investors who are an important stakeholder in project success. We've got 2 battery containers here, with A being the distance between the open sides, where the doors open up, and we recommend this being a distance of 3.1 meters. And this is also to do with fire separation, but to allow for access into the battery modules. Next we have E, which is the back-to-back separation distance. It may look quite small, and we recommend follow the original equipment manufacturer's installation guides, the OEM, as it's their product. And in our cases, we've seen this being as low as 0.15 meters. Again, these products are tested to high standards, such as UL 9540A, which evidences that in controlled circumstances that the fire will not spread to other containers. We then have C, which is the distance between a container and an obstacle, such as a wall or another container. And again, we recommend to follow the OEM's installation guides, but in our experience, this has been around 2.5 meters. This is to allow for cool, clean air to get into the HVAC and properly cool down the system, especially during heavy cycling. And lastly, we have D, which is the distance between the battery container and the MVPS, the medium voltage transformer. We use a value of 5 meters in the basis of a design, but this is really dependent on the type of oil that's used in the MV transformer, as well as the capacity of oil. So again, that's an important factor to check when going through procurement. I'm now going to move on to quality assurance and the importance of QA in contracts to protect the developer. I'm going to start with a little poll question, and by the end of the section, you should know more about all the different types of testing and what their function is. Sorry, carry on. What's up? So to begin with, we have factory acceptance tests. These are conducted at the manufacturer's site and is the first line to detect manufacturing defects in products. This is used to verify that the performance of the battery components, as well as the ancillary systems, such as the cooling systems, operate as expected. And this is before the equipment gets to site. A portion of these will typically be reviewed by the employer or the employer's representative. Next, we have the delivery acceptance tests. These are, depending on the Incoterms, which I'll come on to later, are a test to check that transportation did not cause further defects or any issues. We like to push in contracts for environmental monitoring, and this is because lithium ion is particularly sensitive to extreme vibration as well as temperature and humidity extremes. Once it gets to site, you can check the limits have been breached, and in these cases, you can flag containers that may have performance issues down the line, or in extreme cases, it can lead to replacement or rejection of equipment. Once the equipment has been installed at site, comprehensive commissioning tests are conducted. These tests include active and reactive power testing, frequency response tests, and grid compliance, grid services tests. This is to evidence that the project is compliant with the grid code, the grid connection agreement, and as well as that it can deliver the services it was procured to do. At this time, at a similar time of the project, you also have performance tests on completion, and these are used to verify that the performance is as expected and that it's guaranteed, that it meets the guaranteed or higher values for energy capacity, round-trip efficiency. Lastly, we have the operational phase testing. This is quite similar to the performance test previously mentioned, but this occurs on typically the anniversary of the test on completion. Again, you'll be measuring the energy capacity, round-trip efficiency, but also the availability of the BESS project in the previous year. This is important as it gives insight into the degradation of the battery, and it also can allow you to optimize maintenance to prevent unexpected failures down the line. Now we move on to the investment costs for a grid scale BESS. First, we have the DevEx, development expenditure, CapEx, the capital expenditure, and finally, operational expenditure. Understanding these costs is essential to ensure project viability and to secure financing from lenders. Then the DevEx, that covers the developmental and pre-construction costs. These include navigating the planning permission application with the local planning authority to obtain the actual rights to build a BESS in the first place. This can be a lengthy and costly process with adhering to local regulations and to the local community. In addition to this, we also have obtaining the grid connection agreement, actually getting permission to connect to the distribution or the transmission network. This can be a lengthy process with studies and even in some cases, infrastructure upgrades. Both of these things can vary across the country depending where you are, and because of that, it can make it really difficult sometimes to get access. And lastly, with the land rights, actually buying or leasing the land has a cost, and this comes under the DevEx as well. These costs, to give you some context, by the end of it, you should have a construction-ready project, but it can go into the millions for really large projects. Next, we have the CapEx, the actual cost of building the system. This includes the cost of the equipment, which predominantly composes of batteries, but also has the cabling, transformers, and the control hardware. From our experience, this can range anywhere from $90 per kilowatt hour to $200 per kilowatt hour, and can take up to 60 to 70% of total CapEx. This is based on our experience. However, this The range can be explained by factors such as client relationships with the suppliers, locations of the project, and the actual size of the project to begin with. The CapEx also includes actually getting the site ready for installation, so the civil and the electrical works prior to installation. Then we have the equipment installation and the commissioning, which again falls under the CapEx. Other costs of the CapEx include training, initial spare parts, and equipment warranty at the beginning of the project. I'd like to highlight here that the cost of equipment have been coming down rapidly. The lowest ever tender recently came out in June 2025 for $51.59 per kilowatt hour. And this was for not only the DC product, but also the AC and the energy management system, the control hardware. So this was in China, and they do have access to lower prices, but it shows that the trend is prices are coming down. And finally, we have the OpEx, which covers the ongoing costs of running the system. This is typically covered by a long-term service agreement, which is offered by the supplier on a yearly basis. This includes things such as the performance warranty, performance guarantees, equipment warranties, spare parts throughout the project, and operations and maintenance. Then we have augmentation, the act of actually repowering or adding in new batteries, bring up, in some cases, battery back to 100% of the original capacity. It's critical that augmentation is considered as early as possible in the project because this affects the grid services that you'll procure, your grid connection, and it also allows for costs such as the civil works to be optimized when designing the site. And lastly, we have asset management. Someone's going to need to be able to run this site on a day-to-day basis, whether that's in-house or if it's procured by a third party. And now we move on to eliminating and reducing commercial risks through the contract to protect the developer where we can. So we like to begin with detailed but concise technical specifications that clearly set out the requirements of each party. This is accompanied by a DOR, a division of responsibility matrix, or a RACI matrix, clearly delineating each party's responsibility, especially at key interfaces such as commissioning or installation of equipment. Having one accountable party means that they are taking full responsibility, and in some cases it prevents contentious points further down the line. So it just means it's clearer and better to have it sorted at the start of the project. Next, we have the Incoterms, which I touched on before. We push for delivery duty paid, you can see by the smiley face there, which is to be in our contracts. This means that the seller is responsible for all the costs and risks, including shipping, insurance costs, custom duties and import taxes, until the goods are delivered at site. This means that the buyer's responsibility only begins after it's been delivered and accepted, in accordance with those delivery acceptance tests. And then we have the payment terms. Another aspect of reducing risk is managing the payment milestone of actually paying for the BESS equipment. We recommend that developers push cost-neutral approach, meaning that before the equipment arrives, approximately 50% of the price has been paid, with 50% coming after the delivery. This means that the rest of the payment is tied to successful delivery acceptance and milestones after the delivery, meaning that the supplier is more engaged. And lastly, we have liquidated damages for delay and performances, which are a way for the developer to recuperate losses associated with delays, other extra costs, or lack of performance from the BESS. Delay LDs are applied when equipment is late for a milestone. This is typically for arriving to site and commissioning. However, we've seen that projects with delay LDs split into more milestones with a smaller percentage lead to less delay and better management of the project. Then we have performance LDs, which are applied to the BESS when it does not meet the specified performance, usually at taking over. The supplier will pay a percentage of the contract price for shortfall in technical parameters such as energy capacity and round trip efficiency. Now I'm going to hand back to Andres to speak about the markets and the future of the BESS. I'd like to clarify, on the poll earlier, that in the QA section, the point is that all stages of testing are critical for a successful and reliable BESS, and without one of them, the project doesn't work fully.
Thank you, Harry. Yes, so let's move to market what we think the future of BESS can be. So in the UK, we have some service available, what we call the stack up revenue model. So starting with the capacity market. The capacity market is a power availability market or service in which your plant has to deliver that power in the case that you're being cold. This normally happens when there is a total failure on the grid or a total blackout. Then the government through national grid can request power through to those projects that were awarded contract. This works as in an auction basis. So you have the T-1 and the T-4, and you get awarded a clearing price. Like for example, this year it was £60 per kilowatt per year, with a derating factor of almost 21% for those 2 hours. The T-4, what it means is that you have to deliver your project 4 years after you're being awarded contract. The capacity market is the only services within the stack-up model that you can forecast your revenues, because obviously as long as you can deliver it, you have a fixed contract term for 15 years. We also have the ancillary services, or those called frequency response services. In the UK, we have dynamic containment, dynamic regulation, and dynamic moderation. DC is a post-fault service. DR and DM are pre-fault services, ultra fast. However, the volume of the revenues within this service have been reduced quite considerably. Equally, triads used to be a big thing back in the past. Nowadays, not much. Basically, triads is that time on winter where the electricity operator set the use of the transmission and distribution charges at the highest peak of the electricity. So ideally, your battery wants to be there ready to dispatch when these electricity prices are being at the highest. Then you have your power purchase agreement or PPA, and the REGOs, which are incentives from the government. These actually have increased attraction from developers, especially those that want to have co-located solar PV or wind with PV. Then we move into what we call the BM, the balancing mechanism, and virtual lead parties. The balancing mechanism, as it stands today, happens only at the transmission. So you have the distribution below, and on top of that, you have the transmission level. So if you want to participate on this market, you have to be connected straight to the transmission. That means that you need to have a large system. If you were to be connected into the distribution level, then you have to go through a virtual lead party, which pretty much what they do is to gather all of these small projects together through their license to trade into the balancing mechanism level. In terms of the key service, this is evolving all the time, but at the moment we have the balancing reserve, obligatory services, slow reserve, among others. And through the virtual lead party, what you need to do is for your system to be higher than 1 megawatt in capacity, and then they need to register as a BME unit or have its respective BM ID. Then you have the wholesale electricity market that also happens at transmission level. And this has increased quite considerably from the past, because now we get more projects being connected at this level. In here, is your spot market. You're going to have the day ahead, intraday, and real time. For that, you need an electricity trading strategy and a trading platform. To give you an idea of the volume in terms of revenue per service, back in 22, we had the biggest volume in revenues was from frequency response. And you can see almost minimal. You have some revenues from balancing mechanism, some from the wholesale trading, and a bit from capacity market. Then moving forward to 2024, you can see the frequency response has been reduced quite considerably, while the BAM revenues and the wholesale trading and also capacity market increase quite considerably. So how you do that? And you can do the whole trading of your asset yourself if you have the experience. Most commonly, At least our clients go through what we call operators or route to market providers, the RTM. Some of them like being called optimizers, but I don't like much that term, if I'm honest. But anyways, the point here that these guys, they are the responsible to bring their intelligence in terms of algorithms to follow the market, to make sure that your asset can penetrate those that market and therefore increase revenues for you. There are different agreements, but the type of agreements or trading strategies between the asset owner and the RTM, but the most common ones is your floor price and your tolling agreement. These are considered a bit low risk, one more than the other for the asset owner though. And the floor price, what it does is that you, as an asset owner, will agree a floor price for the revenues that the RTM has to target to hit. Anything above, you're going to share that revenue with the RTM. In some cases, very rare, anything below, the RTM will top that up. Or you have your tolling agreement, which is the most preferred for those risk adverse that or the lenders that you pretty much rent your batteries to the RTM and they will only pay you a flat tariff regardless of what happens to the market. So you're not exposed to the risk of market fluctuation. Or you may feel that you have enough intelligence, experience in the industry that you want to go full merchant and you may just request the services from the RTM under particular fees. To show you a bit, this is an example of the intraday in the spot market in July 30th this year. And this is just pretty much what happens in the stock market as well. You will technically buy electricity when it's cheap and charge your battery, for example, here at 2 in the morning at £58 per megawatt hour, and you then sell when the electricity prices are high or discharge your battery. And this happened at 6 in the afternoon, around £95 per megawatt hour. One very important phenomenon happening now, and this happens in any free electricity market where you have high penetration of renewable energy generators, is that you have negative prices. And this is becoming very attractive for battery investors. Why? Because negative prices, pretty much you're going to get paid for using that electricity. And obviously, this is a no-brainer for your stack-up model. Why the negative prices? Obviously, I don't want to get into too much, but pretty much is the fundamental of Adam Smith of the market with invisible hand controlling the whole situation. You're going to have an excess of generation from the solar, for example, all pumping electricity at the same time, and there is no high demand, and therefore your electricity price is going down quite considerably. So in the UK, we had around this back in 2023, a total of 2.4% of electricity value of the total electricity sold in the electricity market. So moving a bit into the future of BESS, we have technology and duration, which are the key critical points here. Chemistries, lithium ion, obviously is there, but other chemistries are being developed, some in more advanced stage than others. You have the sodium, solid batteries, which your electrolyte is not an aqueous solution if it's not actually solid. Then you have your redox flow batteries or vanadium batteries, which are really interesting batteries for those mechanical engineer minded. And then you have your zinc batteries. Unfortunately, and I'm sorry because I'm quite biased, lithium is going to be the king at least for this decade. Why? Because of the cost. It doesn't allow other batteries to commercialize quite easily. Then on duration, we can see that if we were to see 2021, the most common type was your 1 hour battery with 1.5 gigawatt hour worth of capacity installed. Then the 2 hours, it was around 1 gigawatt hour. But if we move to 2024, it ramped up a bit, almost 3 times, and we have 2.5 gigawatt hours installed last year, 2 hour system, and around 1.5 gigawatt hour only for the 1 hour system. And what is happening is that now we are seeing entering the market the 4 hour system, and next year is going to be predominantly 4 hour system. And lithium ion is also entering into the long duration energy storage, which definition we can debate in another forum. It can go 6, 7, even up to 9 hours. This is not like you can use 9 hours your lithium ion. It will depend on how you optimize utilization. But obviously, as the market is in the wholesale trading, it makes sense to have longer duration to attract more revenue to your projects. And here, I wanted to just to show you, it's a bit tapping into what Harry mentioned in terms of the cost and our experience and experience that we have seen out there in other projects. And this is a book, this is an image and an extract from this book called Monetizing BESS, which I definitely recommend, authored by Schmidt and Staffel through the Oxford University. It's free of charge if you want a digital copy. But the thing is, back in 2023, they actually forecast that the price for lithium-ion batteries, for those using battery energy storage system, they were going to be below the $100 per kilowatt hour mark around 2032. We're not talking about that these estimations were done 10 years ago. It's only 2 years ago. And actually, we have even achieved that, even more than that. I'm not saying that these guys were completely wrong. No, that's not the point. The actual point is that the market for lithium ion and LFP particularly, and the cost has reduced so drastically that it makes it so difficult for other chemistry to share that market. In terms of what is going to look, at least in the UK with services, it's expected that the frequency response is going to be completely depleted, and then it's all going to be balancing through the balancing mechanism, and therefore revenue is going to come through there. As I mentioned earlier, the wholesale electricity market is the one that is going to prevail in the UK, but that may change as well. And your capacity market. Capacity market is a bit of a controversial one because there have been talks as to whether actually the UK needs this service in terms of awarding these contracts. So it might well be removed in few years ahead. And the negative prices, this is very important. It's expected by 2027 that at least 21,000 hours of negative prices are going to be available in the UK, which obviously this is very important for investors and asset owners. So wrapping up, we want to leave you with key points here. We need BESS to meet the net CO2 targets and energy security, which is becoming extremely important with the geopolitical tensions that we have experienced around the world. Fire and explosion risk are becoming more manageable. The battle between the AC and the C solutions continues strong, and it's going to be a very interesting battle. All stages of testing are crucial to a successful project. This is one for me. Lithium ion will be king, and believe me, and at least until 2030. But obviously, other chemistry will make their way. The wholesale electricity market will be the primary revenue source, whilst frequency services will be minimal. Thank you very much for your attention, and for those that got to here, thank you. And we can now move to the Q&A session.
Thanks, Andreas and Harry. That was extremely informative and insightful presentation. I really personally enjoyed that and found it really useful. I'm sure everyone else does, and there's a lot of applause and emojis suggesting the same on the webinar, which is great. So quickly, we don't have too much longer, but what I'd like to do is try and fit in as many questions as we can, and they're starting to come in through the Q&A panel. So what I'll do is I'll just start on those straight away, and then whichever one of you want to answer it, then please just take the floor. So the first question is from Anonymous, but it's what is the life cycle of batteries and what are the environmental risks? Oh, Harry, you're on mute.
So depending on, there's lots of factors that can affect the lifetime of the battery, and this includes the ambient conditions, the temperature that the battery's in, but the primary one is how how many cycles a day or a year is the battery operating. So we've seen this can be up to 20 years on 1 cycle a day, but with increases to 2 or 2.5 cycles per day, this can be 10, 15 years. Then the other question was the environmental risk.
Yeah.
Those, as Andres touched on, lithium, it's mined. So it's not an infinite resource. And, there's environmental considerations with, mining it, processing it, getting it ready in the factories, shipping. So there is environmental considerations when using lithium. And as well as this, I suppose, with projects, typically in the past using internal water suppression. If this gets out of the batteries, it could be, but there's protection measures for that and other measures.
I think just to add the final point there, the other very important factor is the recycling of lithium ion, which is still a very infant industry. Obviously quite important. So what to do at the end of the life cycle of the batteries is very crucial for having a circular economy as well. Thank you.
Really good point. Thanks, guys. Next question is from Amy David, and this is specifically to Harry. What are the different types of oil in MVPS, and which types require bigger distances to the battery energy storage containers?
Okay, I'm not super familiar with the standards. I think it's IEC 60076, which refers to power transformers. But typically, there's 3 cooling systems for power transformers, which are ONAN, oil natural, air natural, ONAF, oil natural, air forced, and KNAN, which uses A-class oils. ONAN systems use convection and circulation to dissipate heat. ONAF enhances cooling by using fans, and KNAN uses natural oils and circulation. And from what I'm aware of, the oil typically has a higher flash point and also is more environmentally friendly. Because of this, I would expect that ONAF with the use of fans and KNAN with a higher flash point would be more suitable for lower separation distances. However, I'd refer to the appropriate IEC standards possible.
Thanks, Harry. The next one's from Elliot Lindsay. Thank you for the interesting presentation. Are you able to comment why revenues from frequency response services have dropped in recent years? That was a point you made in the presentation.
Yeah, sure, I can take that one, John. Yeah, so basically what is happening, because we have a free market, and this is also the tendency in any market outside the UK that also shares the free market principle. Because the grids, they are pretty much basing the services on those projects connecting to the grid. It reached a point that you have too many batteries oversaturating the market, and therefore there is not that need. At the same time, at least in the UK, there is a better understanding of the dynamic of how batteries can be used. And that's, for example, the case on the balancing mechanism, that you're having new services that you can say, well, look, I don't need to pay for these frequency response services, when actually I can manage those through the balancing mechanism angle. And at the same time, at least in the UK again, there is an enhanced way of control and monitoring and managing the grid, where you have more distributed energy resources that you can actually balance that a bit. So all of this put together is what happens on the frequency that you see that they reduce. And the same is happening in Germany. The same will happen when Spain opened the market, and so on. Thank you.
Thanks, Andreas. Next question is from Michael Crowley. What is the round trip efficiency of a lithium ion cell? I think is what he's asking.
Yeah, that's a free consultancy services now. No, just kidding. So we like pushing the suppliers, and I hope we don't have any battery supplier here, so we don't want to reveal all of our secrets. But technically speaking, depends on your project and your configuration. But the most standard one, you can start from 87% round trip efficiency at the point of connection, regardless if medium voltage or HP, including the auxiliary loads, and then you can reduce that or remove the point of reference to where the actual battery is interconnected. You can have 87 or 85, and the 87 is a bit for negotiation, but normally it's agreed contractually the 87%. If you mean the round trip efficiency of the overall project. If you mean the round trip efficiency of the battery container only, the DC, sometimes called round trip efficiency, you can see anything between 92 or 95%, depending on the supplier. Thank you.
Thanks, Andreas. Thanks for that. Next one is, with net zero expected by 2030 and the contract's been awarded on a 4-year install target, are we at the pinnacle of the battery energy storage market, and the market is expected to slow in the next couple of years, question mark?
I'll take that one. Well, actually, let me try to break that question. It's a very interesting question. So we have two critical days, the 2050, that's when the net zero targets are meant to be. Obviously, in 2030, we have a critical one that is following the grid and national grid targets. The capacity market is a controversial point, because whether if it's handy or not, is actually difficult, because if I'm only going to use this as my understanding, I'm not an expert on this topic, but you can see the example of Spain and Portugal. I don't believe that they have a capacity market there. The reason why we have a capacity market is if the worst were to happen, there is a blackout, we can call into this extra power to have power quickly to the grid. It's a service that has been created since 2014. And we have never been in the situation to call because of the good management that national grid have of the grid. And that is the point for debate. If we have never used it, why we need this market when we have, throwing money out there? But it's one of those, the same as with an insurance. You'd rather have it, you're insured, than not having it. So that's the point of the capacity market. So trying to answer if the market is expected to grow in batteries, definitely yes. However, in the UK, you can see now, because different markets for revenues are being a bit, what's the word I'm trying to say? That have not reached its maximum, but there have been a large penetration into these different markets, that probably now you get investors moving into emerging markets, and they see the UK, some of them, because it's a bit of mixed feelings, as a mature market. But for the battery spectrum, and at least for us Blanboz, we see this not on its infancy, but still far away from mature, because you have so many different other markets that haven't even started. Thank you.
Okay, I think we've got time for one more, just to squeeze one more in. I know we're over time here, so but some really good questions. This is an interesting one too to finish. Is battery energy storage suitable for railway applications? For example, storing the electric power generated by an electric train during dynamic braking. And that's asked by James.
Yeah, very interesting, and definitely BESS are suitable for this. But before I say it too light, obviously it depends of what the application is going to be. Battery can work as an UPS kind of system, and you have electric vehicles, and you have also the suitability to transform this into rails. Obviously, if we were to be talking about lithium ion, the LFP as we know it, probably will need to be a configuration of different kind of sources. But I don't see why not it can be used if it's being even used in aeroplanes. again, I'm not an expert on this. I'm more utility grids, but I don't see why, technically speaking, I'm obviously putting the safety risk aside for a moment, why it couldn't work in trains. Thank you.
Okay. Well, I'd like to just say that's the end of the Q&As that have come through. Just like to extend again gratitude to Andreas and Harry for coming on and giving us such a really informative webinar, really insightful, really interesting. And I'm sure going to be sharing this on with some of my colleagues and my network, because it's been really interesting.
Thank you.
So thanks, Andreas. Thanks, Harry. Thanks to the IMechE for hosting this. And did you guys have anything else you wanted to mention before we close?
No, just saying thank you to you, Jonathan, and to IMechE, particularly to Dominic, for giving us this opportunity and for helping us to go through this. It's been very exciting for us. So thank you.
Agreed. Thanks, Dominic, for your organising too. And we'll close there. So thanks, everyone. Have a good rest of your day.
Thank you.